Okay, now let's begin talking about an example of the quasi maximum likelihood function, the distribution that accommodates for normality, and also the distribution that represents true population parameter distribution, still captures the variances. Um, so first, let's start with efficiency comparisons. Engel and Gonzalez investigated the relative efficiency properties of the quasi-maximum likelihood estimator in GARCH models. So when we are estimating GARCH models with quasi-maximum likelihood estimator, where the true conditional distribution is basically a t distribution and the me-specified distribution is the normal distribution. So the true one is conditional standard t distribution, and the me-specified one, for which we converted from maximum likelihood to quasi-maximum, is a normal distribution. We have the results in 20.3. Let's see. Yeah, we'll talk about it. Where the relative efficiency is computed by simulating GARCH 1.1 model for 1,000,000 observations. So simulated for many observations with the restriction of alpha naught, and forming the ratio of diagonal elements. So ratio of the diagonal elements. The population parameters are alpha 1, beta 1, and the GARCH intercept is restricted. The GARCH intercept is 0.1. In computing the variances, the derivatives is computed recursively as, so recursive derivation of the derivatives are recursive with the starter value of the derivative set to 0. Okay, fine. So loop. In 1991 they did that. My god. Beta 1 simulated and analytical results. Same, just a bit different. For comparative purposes, the analytic efficiency ratios from table 1 in Gonzalez are also reported. These analytical results are transformed from the original, where they are quoted as the percentage change in the quasi-maximum likelihood variance over the maximum likelihood variance. So how much is changing in the quasi-maximum likelihood variance from the maximum likelihood variances? For example, Gonzalez and Drost report a value of 150 for the variance parameter where epsilon equals 5. Transforming the number as 0.4 gives the value reported in table 0.23. See, this is it. The simulated and analytical relative efficiency results are in strong agreement. For relatively small values of epsilon, there is large efficiency loss from using the quasi-maximum likelihood estimator in the presence of me-specification. Important when this is actually, I guess epsilon is small. Is it tau or epsilon? This is tau, this is not epsilon. I'm really sorry. Tau is small. Then when we use quasi-maximum likelihood, there is large efficiency loss. But when tau gets to infinity, the two variances approach each other, signifying no efficiency loss. When it grows up, as the extent of me-specification diminishes. Asymptoticity. Okay, so this was estimation, test of estimation efficiency. I really thought this was quite difficult. So now let's move into something more interesting. Multivariate GARCH models. The models discussed so far are univariate, since they focus on modeling the variance of the returns on so we have modeling the variance of the returns on a single financial asset. So we talked about modeling the variance of the returns on a single financial asset. I'm just gonna pause here. So as far as we are concerned, up until now, we modeled the variance of the returns on a single financial asset. A natural extension is to consider a multivariate model to specify both conditional variances and covariances. Okay. So let's talk about multivariate GARCH. Very important chapter. We are beginning from here. The models discussed so far are univariate, since they focus on modeling the variance of the returns on a single financial asset. Okay, so that's what we have been dealing with. A natural extension is to consider a multivariate model and specify both conditional variances as well as conditional covariances. Fine. A simple multivariate specification is, well, have always been there. Y equals epsilon, we know it, where y is the many variables, and the transpose means that they're in columns, in rows, is a n by 1 vector of time series, in rows 1 column. Okay, fine. So here we're talking about many variables, where epsilon is also n by 1 vector of disturbance terms, and v, the multivariate conditional variance, is a n by n symmetric positive definite matrix containing the variances on the main diagonal and the covariances on the off diagonal. Well, very beautiful. We have talked about this. But the convention is, well, the variances are diagonal is adopted to represent the conditional variances. They are the conditional variances and conditional covariances. So we need to find this. Assuming conditional normality, log likelihood function and time t has always been this, nothing new. To compute the maximum, so the last term, we remember that all the time we have been doing that. So to compute the maximum likelihood estimates, two computational problems arise. Now something new. In the case of an M-GARCH model, multivariate GARCH model, so the first is the covariance matrix must be positive definite for all t. This is multivariate analog of univariate GARCH requirement that the conditional variance is positive at each t. Okay, so the conditional variance must be positive, but hey, I understand variance is positive all the time because it's a square. So what we are talking about is that there are no zeros. Fine, makes sense. The restriction needed to satisfy the condition that the conditional variances are all positive at each t. Okay, so they are not zeros. The variances are always greater than zeros, and the determinant of the covariance matrix is also positive. So they have a determinant, which means you can inverse them. You can find the determinant, which means you can inverse them. These restrictions are necessary from a statistical perspective, since the conditional variance represents a covariance matrix. From a computational perspective, a violation of this condition will result in numerical error when computing the term log of conditional variance. Obviously, we can't inverse it. If we can't inverse it, we can't actually continue our calculations. The number of, can't we inverse it? When are they not equals to 0? When there is no multicollinearity. Second, the number of unknown parameters governing the behavior of the variance and covariance in the multivariate GARCH models increases exponentially. Okay, as the dimension. So when your dimension increase, unknown parameters increase. 4 multivariate models are discussed, each of which to a greater or lesser degree deal with these two problems. The VEC model, which is the direct generalization of the univariate GARCH model to a multiple dimension. The Beck model of Engel and Kroner. So what's a VEC model? Directly generalized univariate GARCH model to multivariate. The Beck model of Engel and Kroner, which reduces the parameter dimension of the Beck model and has the advantage that Vt is restricted to be positive definite. So first of all, the number of parameters decrease, good, and V remains positive definite, beautiful. The DCC model of Engel and Sheffield, which reduces again the dimension of parameter of Beck model, thus making estimation. Okay, so again this is a dimension reduction technique. The DECO model, the newest, which further simplifies the DCC model by restricting all correlations to be equal contemporaneously with the result. Okay, so all correlations to be equal contemporaneously with the result that estimation is simplified dramatically. So they are all equal contemporaneously, DECO model, with the result that estimation is dramatically simplified. Beautiful things, right? So all correlations are equal. I am not sure what that means, but we'll get to that, I hope. So VEC is a direct generalization. A VEC specification is the simplest and the natural multivariate analogous of univariate GARCH. For n equals 2 variable, the variance is specified as conditional variance is specified as C VEC plus A epsilon t minus 1 or so. So this is the GARCH parameter, and VEC with t minus 1 GARCH parameter, A, which is alpha GARCH parameter, and then D GARCH parameter, and this is the intercept in case of 2 variables. Okay, so what happens in case of 2 variables? 1 1 1 2 2 2 2 1 and 1 2 is the same as we know, and 2 2 is this coefficients in columns. Beautiful. Okay, this is a representation of VEC, where VEC represents a column stocking of the unique elements of a symmetric matrix. So VEC represents a column stocking. So you have a symmetric matrix stocked in one column. The VEC model does not guarantee that V will be positive definite at each t. This is very important to remember. VEC is a column stocking. It does not guarantee that the conditional variance will be positive definite, even in the bivariate, because a large number of parameters need to be estimated. So we have 1 2 3, so there is 21 parameters we need to estimate. Pretty high specification. The total number of parameters for an n-dimensional VEC model for C matrix n into n plus 1 by 2, for A matrix n into n plus 1 by 2 square, for D matrix n into n plus 1 by 2 square. Quite huge. So that the total parameter of the total numbers is obviously adding these 3 up. For a 3 variable, there is 78 unknown variables, 210. So that is a problem with VEC, quite huge. Let's see what Beck has to say. To impose positive definiteness restriction on the variance, multivariate variance, while simultaneously reducing the dimension. 2 things. We have positive definite restriction, reducing the dimension. The Beck model is, okay, this is the constant term, CC transpose. This is the decomposition of GARCH parameter, and this is the decomposition of the GARCH parameter. where C is a n by n lower Cholesky triangular matrix. Makes sense? Makes sense. It's a lower Cholesky triangular matrix. A and D are n by n matrix that need to be symmetric. Wow. So we have vector matrix specification. For illustrative purposes, the matrices of the Beck model in equation are now spelled out. Okay, so when n is equal to 1 and 2, in the univariate case, you have matrices such as, so bt minus 1 is, 1 1 1 2 2 1 2 2. So this is the first element of non-diagonal element for n is equal to 1 in the univariate case. And vt v1 t minus 1 c1 1. Okay, fine, I understand that. First element. And then vt will have obviously cc transposed a11 a transposed, and the decomposition which gives you this, right? C square, S square, V square. This is just a univariate GARCH model with 3 parameters. This is just okay. So when for the case of n equal to 1 and n equal to 2 is just a univariate GARCH model with 3 parameters. We get a univariate GARCH model with 3 parameters that are all restricted to be positive because they're all squared. Beautiful thing they have found. From that hundreds of huge number of parameters, instead of that representation, we have the univariate representation just using Cholesky, reducing the dimension. So this is how decomposition reduces the dimension. Concept used, decomposition reduces dimension. Beautiful, and no matter how high they are, you still get a univariate GARCH. So when we have n equals 2, keep growing, no problem, they are the same. Vt is replace the information, replace the information. So we have 11 parameters compared to 21 in VEC because we are doing decomposition. Still lower. The number of unknown may be further reduced by restricting A and D to be symmetric. If A and D are symmetric, in case of A and D being symmetric, important to remember, when A and D are symmetric, then these are equal to each other, so they are 1 when they are symmetric. The off diagonal elements equals to each other. Okay, so when we have symmetric in page 32, a very important condition, if diagonal elements are symmetric, number of dimension drops more and more. This is constant, so we have zeros. In case of non-constant, that equals 1. They're symmetric. So parameters actually reduce more. So what did we do? We assume these to be lower Cholesky decomposition and decomposition. This is the equation. Beautiful. I just saved the highlights, so we can do the restrictions. We can test the restrictions with an LR. Another class of models is to assume that the covariance is constant. Okay, if they're not equals, they can be zeros. In case of asymmetric, when the covariances are constant, so first test is when they are equal, they're symmetric, and if they are constant, they can be asymmetric, but they'll still reduce the dimension. Beautiful thing we learned. So Beck estimates of conditional variances, the covariance and the correlation of the changes. Variances, so we have the leptokurtosis captured. Good. Beck estimates. That is absolutely stunning. Okay, bivariate Beck model of interest rates, an example, we'll do it. So we have y1, y2, and this is the equation of interest. Now y1 is respectively the daily changes. We know Beck is stocking in columns. T and y2 T is daily changes on 3 months and 1 year zero coupon bond, 2 variables. So gamma CAD, log likelihood value of, okay, so log likelihood function. So when we estimate this parameter with the given information, estimated parameter matrices, that is the results, these are the results given the information, the data. The time series plots of the two conditional variances. So two conditional variances and covariances. What are the variances? The time series plots of the two conditional variances and the covariances, right? Variances, conditional, two conditional variances and correlation, variances and covariances. The time series plot. So we just take a plot of the variances located diagonally, covariances, and the condition are given in figure 20.6, and this is the conditional correlation. So conditional variances located diagonally, covariances located off diagonally. When they are not there, they become symmetric. Have a look just to revise where the variances lie and where the covariances lie, right? Okay, so here it suggests that diagonally variances locate, off diagonally covariances. So you just draw a time series plots with that, and conditional correlation is also given by this. A test of constant covariance between two interest rates is based on estimating the model subject to restrictions. Is the covariance constant? Just set against restrictions. The log likelihood value, there are statistics, fine. So this is the example. The dynamic conditional correlation model. So what we learned is Beck stocks information in columns. Beck, which is quite easy, reduces dimensionality. We have constant to be represented with a Kolesky decomposition. Others are just decompositions. Half the parameters become half. And how do we do these things? Basically, when we estimate this reduced parameter, we automatically have, with the given data, in a bivariate case, we already have variances and covariances. We can plot them. We still have the conditional variances. So one with respect to other. What is the variance? Good. The dynamic conditional correlation model imposes positive definiteness on VT and achieves a large reduction in the number of parameters. The dynamic conditional correlation model imposes positive definiteness. So the dynamic conditional correlation model imposes a positive definiteness on the residual VT and achieves a large reduction in number of parameters by specifying univariate conditional GARCH variances together with the, okay, I don't understand it. One more time. The DCC model imposes positive definiteness on the conditional variance, fine, and it achieves a large reduction. So number of parameters reduced by specifying univariate conditional GARCH variance together with the parsimonious conditional correlation matrix. How? You impose a positive definiteness. The model imposes positive definiteness. Up to that point, I understand. Then what happens? Okay, I'm feeling a bit hot. So to reduce the model, Univariate conditional GARCH variance is togethered with parsimonious conditional correlation matrix. Okay, fine. Is being specified together. The conditional covariance matrix. Conditional covariance matrix is recovered from, we have a conditional correlation S and S. We are familiar with S and S. Okay, conditional covariance matrix. We are kind of familiar from S and S from structural models. Structural, you see, I think var and SVAR models. SRS. R is n by n conditional correlation matrix. S is diagonal matrix containing the conditional standard deviations along the main diagonal. So when we have conditional variances, we just square it, setting this 0. The covariance is set to 0. So this is diagonal matrix. Beautiful. So this is DCC model, right? The conditional variance of univariate GARCH representation. Okay. So first, conditional covariance matrix is how this is. V is SRS, and variance is the GARCH. The specification of conditional correlation, on the other hand, is diagonal, is a decomposition. Q has GARCH 1 1. So first we find Q with GARCH 1 1. What is Q? It's a function of two unknown scalar parameters, also and unconditional percentage residuals. Unconditional covariance matrix. So it has Z. Z is V by sigma, epsilon by epsilon by sigma, to which is standardized residuals. Unconditional covariance matrix of standardized residuals is located here, as well as alpha and beta. With that we have Q, which is the GARCH 1 1 specification, and when we decompose Q, we get conditional correlation matrix. GARCH is simply separated, and from R we get S. So SRS gives us conditional covariance matrix. Fine. So which is given by this. This is an important equation. Special case of DCC model is the constant correlation matrix. When in case of alpha and beta are 0, there's a different thing. So bivariate DCC model example. So estimate GARCH 1 1 model with two assets. This is just GARCH, and construct the matrix. Fine. First, let's find the standardized residuals, which is S inverse U. So 1 by sigma 1, 1 by sigma 2, 2, and we have constant residuals. With constant residuals, let's find Q, matrix of correlations. Beautiful. So first standardized residual, then Q. Use the result to construct the elements of the matrix Q using a simple GARCH 1 1 specification, but a conditional correlation. Now let's look for conditional correlation, and with this information let's find Q's. These are the equations for Q's. Constant portion, correlation portion, arch, GARCH. Fine. Construct matrix of conditional correlations. So this is specification, and then the matrix of conditional correlation follows this equation. Then you estimate conditional covariance matrix. My God. Okay. And that gives you a DCC model, right? 5-step process. bivariate DCC model for a two asset case, dynamic conditional covariance. Maximum likelihood, let all the vector be theta equals theta 1 and theta 2, where theta 1. So this is a very small parameterization. Then half log SRS, sigma squared is SRS variance. Big V is SRS, fine. Using the results, expression is becomes this. This becomes your log likelihood function, where Z is equal to S is equal to V by Z. So Z is equal to is a standardized variable. Adding and subtracting will give you something like this. Gaussian correlation. Full log likelihood function is this equation. So many equations basically. Okay, gradient and Hessian is also there. So can be used to maximize with Beck. Just like Beck, we can use standardized equation. Unknown parameters in 3n plus 2, very small amount is two-step estimation. In case of large n, we have in the first step log like is with respect to GARCH. S is the power of diagonal elements into n separate components. In case of large parameters, two-step estimation, and for large n, we do this. Correlation parameters. My God, this is really huge. Okay. I'm kind of losing patience. In the first step, the log likelihood function is maximized with respect to GARCH, since S is a diagonal matrix. So we have the product of diagonal elements only. The log likelihood function decomposes into this, and the volatility parameters in each GARCH can be estimated individually. The second step involves maximizing to obtain consistent estimates 20.70. Maximizing GARCH parameters by solving 20.69 was this and this, where this is the GARCH and contains GARCH and correlation parameters. This contains GARCH, this contains GARCH and correlations. Okay, and the correlation parameters is maximized, and this is the log likelihood function. Coefficient, because the full log likelihood function is not maximized with respect to all the parameters. This occurs in the second step, ignores the term in the first element of the gradient vector by treating the volatility parameters as fixed. Moreover, the two-step estimate is consistent but not asymptotically efficient, because the log likelihood function is not maximized with respect to all. This occurs as a second step ignores the term delta in LT by delta theta 1, d theta 1 in the first element. In fact, just the standard errors on theta 2 that are not correct. Okay, whatever. So this is the process of finding the correct standard errors. And estimated parameter is replaced with theta with G2 as to derive the correct standard errors. Hessian is block triangular. Why are we not getting correct standard errors? Second step is ignoring a term in the first element of the gradient vector by treating the volatility parameters. So this term ignored means volatility parameters are fixed. Moreover, standard errors obtained from estimating are not correct as a result of treating theta 1 as fixed at the second step. Okay, because this is fixed. It is in fact just the standards on theta 2 that are not correct, because the standards on the volatility from estimating Gaussian separately in the first step are correct. So this is also theta 2 is not correct. So correct standard errors is found with this. Hessian is block triangular. From the properties of partitioned inverse, it follows. What is the partition inverse property? I'm not sure. Whatever it is, something like that. Defining is the outer part of gradient matrix. Kind of like have to have all these equations in hand. It's not easy. Correct covariance matrices are two-step estimators. Block diagonal quasi-maximum likelihood coefficients are from each GARCH equation, also not only in the special case. So it's a quasi-maximum likelihood covariance. So just like this. DECO, dynamic equicorrelation model of Engel and Kelly, is that the unconditional correlation matrix of systems of the financial returns has entries of roughly similar magnitude. No? Yeah, see how long are we going here? Still recording. Okay, fine. The correlation of DCC model are therefore assumed to be equal contemporaneously across all but not over time. Okay. So DECO is an increase on DCC improvement, make it more difficult. So restrictions are these where average correlation, the RT2n by 1. So this is just a loop. Fine. Correlations are over here. Diagonally are no covariances are 1. Average correlation at time t. The advantage of DECO restriction on the correlation matrix is that as n increases, it becomes easier to maximize log likelihood function corresponding to the correlation component of DECO. So DECO restriction is DCC. Rewriting these restrictions makes it easier. Okay, identity matrix. We get an identity matrix, and this is ON ones and identity. Good, simple. Identity matrix and ON is the matrix of ones. This form of the correlation matrix is the following analytical property, where R is simply this and R inverse identity and ones. Substituting these expressions simplifies the computation of log likelihood function, since now large determinants of inverse need to be computed actually. So DCC is a bit difficult. So application, DCC and DECO of United States yield. So there is an information when we have daily observation in units, zero coupon yields have 1, 2, 3, 4, 5 maturities, 5 yields. The data are from 6 years. So first, the parameter estimates of individual GARCH, constraint in the unit circle, then so first let's put them in unit circle, then untransformed all different of the appropriate standard errors. First constrain them to be within unit circle, then at the end untransform them, and then the parameter correlation significance, there it is given with the standard errors. The result in this, the correlation parameter alpha and beta is significant for the DCC model, alpha and beta, whereas just estimate of beta is a DECO model. Okay, so alpha and beta across variables are significant, but for DECO just beta is significant, which means the GARCH is significant across time. Correlation DCC model at 0 gives you log likelihood function. So constant correlation test can be done. joint test, running a joint test, each 0 means reject, null that there is a constant correlation matrix. Large degree of similarity between two sets of estimates. Comparison gives you a large degree of similarity. A plot of the average correlation of the 5 interest rates model given stable over sample varying between. So figure 20.7. Deco estimates give you volatility being average correlation of all these bonds are stable, which is important information. A time varying volatility of S bar model. So S bar model, structural bar model. Let's see what is short run restriction. Structural shocks to have time varying multivariate GARCH model. To have time varying volatility method. Let YT following is the VIX index. Okay, so we're talking about the VIX index now. This is an important example. The VIX index, which is a measure of volatility constructed for European put and call option prices, such that at any given time it reflects risk neutral expectation of the integrated average over the next 30. Oh my god. VIX index measures volatility constructed from European put and call option prices. First, that in a way, at any given time, it will reflect the risk neutral expectation of the integrated variance averaged over the next 30 calendar days. Okay, so taking 30 calendar days average, which is put and call option volatility average. Okay, so risk neutral expectation. The on-off run units just 5-year spread, which provides a measure of liquidity in the market. This is the first index, VIX index. Then the on-off run US 5-year spread, which is the liquidity measure. Then a swap rate, a repo spread, which is measure of credit spread, default risk. So many multiple type of okay. Consider the following dynamic structural model of YT. Okay, fine. GARCH model, structural parameters with beta not having coefficients of unity. This is GARCH model. This is the structural model. Okay, fine. Beta I are many matrices of structural parameters with beta naught having coefficients of unity down the main. So when we are talking about beta naught, we have ones in the main diagonal to represent usual normalization. K represents the order of the lags and U is a vector of independent structural disturbances. Each has a GARCH conditional variance in the with conditional variances given by the diagonal elements D. The var is this. We are familiar with var. The var parameter related to structural parameters is this. Fine. For all I, beta not inverse beta I for all I, we know that. var disturbance is, this is we studied before, SZT, where S is root over D divided by B, root over D by B. Root over D by B ZT, root over D by B ZT, U by V. So var disturbance of time varying covariance, unlike structural distance, this matrix is not diagonal. It's not a diagonal matrix provided that beta naught and hence S are not diagonal, in which case the volatility of all factors has an effect on all variables. So it's contemporaneous relationship. To identify the parameters of the S bar, the following short-run restrictions. Okay, if we put short-run restrictions on beta, once these are just the short-run restriction. Parameters of S bar, interpretation of structural shocks. So doesn't impact on the library as given by the last row in beta not inverse. So what are we talking about? All factors should impact LIBOR, so other factors should not. So these are restrictions. Fine. One period, 5 period, 20 period shocks. Meaning is to compute orthogonalized impulse, which is traveling through the conditional variance matrix T. The result of the one period variance convert time. I don't know the interpretation. So the variance decomposition for 1 period, 5 period and 20 period shocks are given. These decompositions are time varying, as beta naught inverse root over d divided by beta naught is used to compute orthogonalized impulse responses, which is time varying through the conditional variance matrix T. The results of the one period variance decomposition over time for the United Kingdom LIBOR spread given in the first row. Key factors are the idiosyncratic and broader liquidity factors. This progressively increases in importance. Okay, so this is kind of like a variance decomposition using GARCH. Okay, so that ends. We'll look into these models in practice. Thank you.